In this video, I will explain the very important questions that are like asked many times, and these questions are that if I'm running the case with like a complete cylinder, all whole full geometry, so can I reduce the size of the geometry? Let's discuss about this thing. Okay. So the first case is this one. Second case is that we can actually make it like we can use a benefit of symmetry. So I can make it like 180 degrees. I can make it 90 degrees. So let's run the one case with 180 degrees like only half. And in the third case we will run the case as the 1/4. And the fourth case I will take the one sector that is going to be the like 30 degrees. And then in these cases I will use a symmetry boundary condition, and here I will be using the third and fourth. They will be used by the second third will be I will use the symmetry condition on the now two parts here in the one plane only. Here I will be using the periodic condition. And the fifth case is going to be the axisymmetric case, means that we will take the only one plane, and that is from the if the geometry is like this is my center line. So we'll take only this plane. Okay. And the requirement of the center, axisymmetric, this is axisymmetric case, we only model the single one half plane, and requirement is that, and this is like shifting the problem from x, y, z coordinates to from Cartesian to cylindrical coordinates. So this will be in the r, theta and the z. So r is radial, theta is like a theta direction, and the z will be z, which is the axial direction. So what we are doing here is that we are assuming this thing, and this thing was we already discussed in the theory part also, that there is no change of the fluid velocity along the one is like we already know this is there is no change du means x velocity with respect to y. This is the condition when the flow is fully developed. Second is that there is no change along theta direction, means that the flow is same exactly on the each and every location on the radial direction, on the same radius, but radially on the every theta this is same flow is there. Okay. This condition means that we have the axisymmetric flow. So we can solve this problem if I convert my Cartesian coordinates to the cylindrical coordinates. So now I can solve this problem in the two dimensional as well. Okay. So let's solve this proposition and see what differences we do get. Okay. So here I'm going to be using the medium mesh file, and I will click on duplicate. Okay, the first I will go with the half model, then the quarter model, and then the next cases. Okay, and I will be plotting the center line velocity. I will plot the pressure drop, and I will plot the relative velocity profile. So these three things should give us a fair idea, and also you can plot the skin friction coefficient as well. Okay, so in the geometry, double click here. Okay, so what we can do here is that there is a option of symmetry directly in the workbench. Okay, so number of planes you can choose here. So here which plane we can use, we can use the YZ plane, or we can use the ZX plane. Okay, so let's try with the YZ plane. Okay, apply and full model and all bodies, export symmetry, yes, click on generate. Okay, so in a similar way, when you are going to be making the or you can make the symmetry on the other plane as well. Okay, and when you are going to be making the a quarter model, in that case you have to use the two symmetries. Okay, and second plane definitely is going to be ZX plane, and here we will click on generate. So you will get the only quarter model. Okay, so right now just use the one symmetry and generate. Okay, so just we need to confirm that do we have the name selections properly done. So inlet is here, wall is everything is a wall, and okay, let's make it opaque, and the outlet is here. Okay, so everything is all right. The only thing that we didn't take care is the symmetry boundary condition itself. So select the face selection or surface selection, and then choose these three surfaces. Okay, right click here, name selection, and it's only one symmetry, so you can put the one name symmetry. Okay, and click on generate. Save the file, and I will use exactly same mesh, but this time what will happen is that I will use the same diagonal mesh, but on the these two sides, these sides. Like we use 10 cells here, I will use here 5 cells only, because it's a half of the length of the full square. Okay, so that should give us the compatible mesh, half the cells, we have the 21,000 cells for the 41,000 cells for the medium mesh. So if I cut the model half, so that should give us, ideally speaking, around 20,500 cells. Okay. So, but the benefit is that this is the mesh will be like a half, but this will give us a data results close to the same as the full case. Okay. Okay. So sweep method is there selected for everywhere for the 4 bodies. Edge sizing is defined here for the 4 edges. So we have to select the 2 more edges which are on the now symmetry plane. These ones also should contain the same exactly data. Okay. Now I should be worrying about that which edges I should be using for the reversing the bias. So this is it should now go it should have the more gradient of the mesh towards the wall, but here it is opposite. So select with the control key pressed and apply. Okay, this is corrected. And here as well. Okay, so I think we missed these these lines from the edges from the selection. So you have to press the control key and then select them. So now 8 edges are there, and their biasing is opposite. So you can correct that one. Okay, or you can directly reverse the second biasing type. You can go to the second biasing type if everything is in the opposite direction. Now it is corrected. Okay, and third size is over here. Okay, third size is over here, which is now this edge should not be the part of the a specification of the mesh here. Okay, so they should contain the half cells here. Okay, sorry here. So these should contain the 6 these 6 edges should contain the 10 cells. Okay, this is okay. So now I need to define another a sizing, and that will be for these edges. Okay, because now they are half the size, so they should contain the half the number of cells. So make it half. So this will be the 5 divisions. Okay, now simply click on generate to generate the mesh, and okay. Okay, behavior should always be the hard. Okay, so make it no and hard. Okay, here is the hard behavior. It's the hard behavior here, hard behavior here. Okay, so click on generate. If there's some problem in the biasing, that's a different thing. Okay, that we can correct. Okay, so there's a problem in the biasing, so let's correct it. Okay, so make it transparent. So this is okay. Okay, then if everything is all right, then delete the old mesh file and then create a new mesh file again. Okay. So I think might be the edges are not given there. Okay, this is a problem. Okay, okay. So these edges are not selected actually. So I will go to the edges and select these edges as well. So make sure everything is selected. So this edge, how many edges are there should be there? There should be like 8 edges. Okay, now click on generate. Okay, so now number of cells are not exact. Okay, they're exactly 20,500. So it's a good thing actually. Okay. So it's the same mesh as the full mesh, but only thing is that now we have the benefit of using the half mesh size here. Okay. So you can save the file and you should also update the mesh file. Okay. This is like a half model. Then I will go for the quarter model. And then one case will be the we'll just leave this idea that will be done in the like end of this video. Okay. So what I'm doing is that I'm going to be updating my file. Okay. Okay. Now right click here and click on duplicate. Okay. You can rename here and you can say this is the half model. Okay. So rename. Okay, now double click on the geometry. Okay, simply modify the symmetry condition. Okay. Sorry, not here, but this symmetry. So this will like now two planes will be for symmetry and second plane is going to be the ZX plane. Okay, click on generate and just make sure that we have the symmetry condition there. Okay, this is one symmetry only. So right click here and rename. So this is symmetry 1 and symmetry number 2 is on the bottom side here. So name selection, there are two surfaces actually are there. So it's a symmetry 2 and click on generate. Symmetry 1 is here, symmetry 2 is here. So you can save the project file and then double click on the meshing to open the meshing. So this time be careful about the where we have to like half the size of the mesh there. Okay, definitely on the half geometry. How geometry mean once you like split the with the help of symmetry command, that geometry now is not more like it's not no more it's like a full geometry. So now it's half version. Okay, so this time this will be now extended to the second part as well. Okay, so these diagonal edges will go directly there. So there's no exception here. Okay, so two more edges which are here and here as well. Okay, so we should take care of the reverse biasing as well. So let's reverse the biasing here. Okay, so now we need to modify this edge. Okay, now go on the other side. Okay, so we have the problem here as well. Okay, so don't worry. So I will select these two edges and apply. So now we have the three edges for the reverse biasing. Okay. Second edge is here. Now this contains the half geometry. So what we can do is that we can now actually delete this from here, and here I will now include these edges also into the sizing here. Okay, so be careful. So these are the 1, 2, 3, 4, 5, 6. And then the 7, 8, 9, 10, 11, 12, 13. Why 13 here? Why not the one, two, three, 4, 5 and 6? Okay. Okay, this is wrongly selected. Okay, so 5 are there, this is same, and these are the diagonal edges. Okay, so let's create the mesh, and it should be like a half of the 20,500. This will be like a 10,225, 250. Okay, that's okay. Just check the mesh, everything is all right. Okay, we do have some problems, so I will define them along the length. So here I will now again go back to the wireframe mode and select the missing edges. So all are selected now, I think. Okay, now you can generate the mesh. Okay, so update the mesh file and save the project. Okay, now double click on solution. Okay, here you can correct the, okay, I think everything's all right. So we can check the solution monitors and confirm everything is all right. And laminar flow is there, and material properties are correctly defined. Everything is okay, I think. Okay, so you can run calculation. Now definitely with half model, half mesh size, the solution should converge very quickly. Okay. Okay, I'm stopping solution here, and then close the fluent. Okay, and then I will be running the second case. Okay, so there's a one confusion that we have to correct the mesh settings there, and okay, I think there's no issue at all. So you can display the mesh file. Okay, I think everything is all right. Okay, so you can now run the calculations. Okay, so I'm stopping solution here as well. Okay, here I will duplicate the I will duplicate. Okay, this is the, okay, same we can use here. So duplicate. Okay, now I have to put the solution from all three cases. This is like a complete full geometry 360 degrees body is here. Second case is here. The half model third case is here. This is the full model, and one is a half model, which you can see here, and one is a quarter model. So they are giving us a similar velocity profile. Definitely in the quarter model you cannot see the the bottom half, okay, and this is symmetric actually, so bottom half will be exactly same. Okay, so what we can do is that we can go to the plane number 1, and okay, polyline number 1 is also okay. So let's go to table number 1, and here the value for the half model is 0.16025. What about the full model? The same values. And what about the quarter model? Same values. Okay. In a similar way, I can go for the coefficient of friction, and all of them are giving us same result. So it means that running the like a quarter model will be more economical. Okay. Okay, one more thing is that when I was running the case, I didn't take care of the symmetry boundary condition. So, are the fluid is applying the symmetry condition by itself or not? So, I have to check that thing. Okay. So, first check this thing and then we can comment. Although from results, it seems like everything is all right. But let me confirm this thing one time. Okay. Okay, I'm going for the display of the mesh with the default colors by the type. Okay. So, okay, this is like satisfied myself that the color here is a yellow. Yellow means that's a symmetry. So, what is happening here is that we didn't specify the boundary conditions yet types here, but from the name, the fluent inferred that the name should be the symmetry. So you can like confirm that thing as well. Okay, otherwise you have to put it like it might have been the wall. Then you have to change it from here. For example, wall, you can change the wall to the symmetry from by clicking on the different type of the boundary condition. Okay, so this is okay. One more thing is that if you want to see the like a result in the fluent, then in that case, for example, I'm displaying on the wall and I'm only seeing the quarter model. So how I can display the full model? For that, you have to go to the view menu and then click on the views and then click on the symmetry one. You will get the half model. If you click on second symmetry, you will get the full model. Okay. This is the way actually you can get the full model in the fluent. And in the CFD post, the things are slightly different. Okay. So how I can get the full model here from the like quarter model or the half model. So I will give you the demo on the quarter model. So this will be true for the half model as well. Okay. So for that, what we have to do is that there is the instance transform. Okay. So insert that one and instance transform. And here, which transform we are going to be making? We are going to be making the reflection. Okay. So the reflection from a plane. So apply. Okay. So now we have the like instance transform. How many interfaces you want? You want the two. So it's from the reflection. Okay. So it's a reflection is now XZ plane. Okay. And how many copies we are going to be getting? We are going to getting the 2 copies here. Okay. So now go to the vector plots, which are here. And here you have to see the view and use the instance transform 1. Okay. So now let's see which is going to work very well for the like a make it half model at least. So I will go back to the instance transform and here Okay, so you can see now we have the like half model here. Okay, and same thing goes for the our like a wireframe. So wireframe also needs the same application of the instance transform, and you can see the half model here. Okay. Okay, and if you apply the like number of instance 4 and make it full circle, okay. If you make it 2 instance, then this will be the half, okay, and 3 and 4. Okay, so okay, now go back to the other like profiles here. So center line velocity, let's compare them. They are also okay. Pressure values, they are also same, exactly same. Radial velocity profile exactly same. Okay, and so everything is same. So it means that we can now run the case with the quarter model. So we can save our resources by the 1/4. Okay. Now let's run the last case. That last case is with the axisymmetric model. Okay. So close. Okay. So here we are going to be like get the third case, that is the 2D case. Okay, so first thing is that click on the geometry and make it 2D. Okay, then double click on geometry. So the geometry making procedure is slightly different than the 3D case. Okay, so we will not use the 3D features, only one sketch, and that is also like a rectangle, and that's all. And second thing is that the geometry should be made, the axis should be along the x-axis, and the second axis should be the y-axis. And secondly, the z-axis should be 0 value, means that you cannot even like translate the plane. Okay, and also you cannot like make geometry on the other side of the like it should be in the first quadrant. Okay, so simply put a line, and your line axis line should be exactly on the x-axis. So this should be like a closed, like you can make the rectangle. This will be much easier. Okay. Okay, so put dimensions for the length and the width. So it's 40 meters, and diameter was 1 meter, so radius would be the 0.5. That's all. And now I will go to the concept menu. From here I will use the surfaces from sketches. Okay, so one sketch, one surface, doesn't matter. So here you have to choose a sketch number 1 and apply and click on generate. Okay, so now we need to define the boundary condition. This time the boundary condition will be defined on the edges. Okay, so right click here, name selection, and this is the inlet. This one is the wall, and here is the axis. And here will be the outlet. Okay, that's all. And now I will double click on the meshing, and this time the meshing distribution will be exactly same, like 50 cells across the length, but diagonally, because now this contains the inner cylinder, like inner box, and the diagonal edges. So we will be making the number of cells around let me check what was there on the like 3D case. Okay, okay, so diagonally the number of cells are 18. This is for the medium mesh. Okay, and here, so I will calculate the number of cells on this direction. So 18 plus 5, they will be 23. Okay, 23. Okay, 23, and definitely with the biasing on the towards the wall. So here, and number of divisions like this one will be 50. And you make sure that the hard behavior is is enabled. And here we should have the biasing as well. Okay, let's define the 10 factor, and you can put the second way of biasing, and also confirm on the other side. Okay, this is like on the other side, so this is wrong. So we have to use a reverse biasing to correct it. Okay, now simply click on generate mesh. Okay, one more thing is that I should use the face meshing. Okay. Okay, now you can click generate. Okay, this will now will be quickly. Okay, so this is done now quickly, very quickly here, and I don't want the very fine mesh in the boundary layer. This is a laminar flow, and we are not taking care of the Y plus. So what I'm going to do is that I'm going to okay, sorry. So this is like a not bias factor but smoothing ratio. Okay, so let's make it 5 and click on generate. This is okay. And how many cells are there? There are the only 1150 cells are there. Okay. So you can update and save the project file. The question would be about the post processing. So I will answer this question also. Okay. Double click on the setup. Like here the one core will be enough. 1100 cells are nothing. Okay. Okay, display the mesh. Okay, and in the models I will choose as the laminar flow, and from the journal we have to change it to the axisymmetric. Okay. So make it axisymmetric, and in the materials I will be changing the density and the viscosity. Density is the 1 and the viscosity is equal to the 0.01 kilogram per meter second. Okay, click on change create, and the boundary condition we have to confirm that x's are x's, and at the inlet the boundary condition value is 1 meter per second. So 1 meter per second, and then in the monitors I will not be I will make it no criteria here. So it will only stop when the it is run for the number of iterations, or when I stop them myself, or you will stop that yourself. Okay. So now run calculations and run it for 1000. It will converge before that, but let's put the more number of cells there, more number of iterations there. Okay, there's a problem. So stop here and make the algorithm from coupled to the simple, and again initialize the solution with the hybrid method and run the case again. Okay. This time this will be very, very quick actually. Okay, now we can stop here. Solution is almost converged. Question is that can we post-process the data in the with the other files of the 3D cases in the CFD post or not? So let me try to that answer. Okay, otherwise we have to make it separate. Okay. Okay, and the benefit is that where one extra feature that is in the workbench is that in the workbench when we make the files like this, they actually can make the 3D like a 2D case to the like a, it will like a if this is axisymmetric case, then what will happen is that it will just extrude the mesh in the third dimension in the theta direction by 5 degrees. So let's try to drop that solution on the results here and then double click here. Okay, so it will now read the data file there. Okay, so no, not yet. So let's close and then again open the CFD post. Okay, so this was, I was telling you that this will make it 5 degrees along, or this is what I have read somewhere. So let's check it. Okay, so every file is there and we will just synchronize the views here. Okay. Okay, so now I will be double clicking on the vectors and click on apply. Okay, so range is global, is a local now, and symbol is okay. This is okay. Okay, definitely this is not possible in the 2D case. Okay, so let's go with plot of the center line velocity. Okay, so double click here and you can see that all four cases, okay, they are exactly showing the same behavior. Okay, pressure also showing the same behavior on the center line. The radial velocity profile is showing the same behavior on the over there. It means that everything is all right. Now in the table, something might be a problem here, because we don't need we don't have the a curve there where we can use a length average. Okay, so this will be a little bit tricky here. Okay, so for this is okay. Medium mesh will also work and quarter mesh will also work. So I need to make a 1 point there. Okay, so this time I will make a now let's say that I have the one plane that is created here. Plane number 2 is created on the 0, 0, 0. Polyline 1 is with the wall and the plane 1. So okay, and plane number 2 is here. Polyline number 2 is with a plane. So do we have the ISO clip for every case or not? Okay, let's make a 1 point. So what we can do is that we can make a ISO clip, and this ISO clip will be the intersection of okay, this will be the ISO clip. Okay, before that I need to make a polyline. Okay, so this intersection of the between the center line and what I say. Okay, let's make a center line first. Okay, so insert and location, and the line will be from 0 to the 40 meters in the Z direction. Okay, make the points as 50 here. This is axis line. Okay, or we need line somewhere else. No, I think that we need the line, vertical line. Radial line will be enough. So radial line is already there. Okay, this line is there. Okay, so what I'm suggesting here is that I'm going to make a ISO clip from the line 1. Okay, so from the line 1, Okay, 0 and 40 here. Not the 40, but make it 0, and this will be the at minus 0.5 and plus 0.5 and 35 meters. So line number 1, and then I will make a ISO clip here. Okay, so insert, and this is going to be the location, and ISO clip from the line number 1. Okay, my parameter would be the y direction actually. So here. Okay, this one. Okay, now what I'm trying to do is that I'm going to use intersection between the cylinder surface and this line, and probably we are going to get the point if we can. Okay, so I'm going to create a point. Okay, and method is that okay, this is not possible, so let's put the ISO okay, let's make it polyline. Okay, so this is going to be the okay, we don't have the option to use anything else, so okay, let's use a point directly, but point will be like may not be directly on the that surface there. Okay, that's not possible. What we can do else, we can use the like ISO clip. Okay, let's make a point directly. Okay, so 35 and the y will be the 0.5. Okay, here. So now I can use the table option, and I can use the right click here function, and this will be the this is going to be the which we can use the like okay, use expression, and okay, now I think this is not possible actually to get at the point. Okay, so we need to like but we can get the idea that from the like this plot here, that this is also having the same values. Okay, so from here we get the idea that this will be having the same data. Okay, so there's no point of like going for the complicated things here. Okay, actually I found the solution. The problem was that when we were making the line polyline, this is from the plane number 2, but plane number 2 is at the like Z35. Okay, but when we have the like axisymmetric case, then axis along the Z is along the X axis, but in our other cases the axis was along the Z axis. So one solution is that you can like rotate them and make them compatible with the 2D axisymmetric case. Secondly is that I made the third plane, and then I made the polyline that is intersecting the wall and plane number 3. So I got this line here. Okay, this line over here, this line. So now I am going to create the table, and in the this table I am going to use the same function, that is the area line average, and what the expression, that is the coefficient of friction, and where this is location would be the polyline number 4. Okay, okay, let me check it. Okay, polyline is with us, and let me check the table number 2. Okay, so it is giving us the some problem here. Okay. If I make the same thing here, okay, this is a how, no, sorry, this should be like a this thing. Okay, now it's okay. Okay. So if I make it as a fixed one, then the data is almost like a 0.16. So now I think this is done correctly. So now we can like close this topic, and now you exactly know that how to post process the 2D cases. Okay.